All right. So, yeah, I sort of get frustrated with kind of misinformation out there. So this is intended to kind of demystify a lot of things that you read about. So with only 45 minutes, I have to go extremely quickly and certainly skip details of the math and certainly no security proofs. But there's all these things that if you try to learn from the literature, the papers are incomprehensible. So they're so full of notation and security proofs and so forth. So I'm going to explain what problem is being solved, an intuition into how to solve it, and whether it's actually practical enough to care about it. So I gave a much longer version of this to colleagues and let them choose the topics. So you can blame them if you don't like which topics are here. So I'm going to cover the ones in red, and the ones in black were less popular with my test audience. So, oh, and this also, right, okay. So you'll see. Sharing a secret. So I like to talk about this. It's not like a brand new thing, but it is just so incredibly cool. And when people understand how it works, and it's like not hard to understand, then their eyes light up. So I'm including that for that reason. So the problem is you want to make n backups of a secret S, and you want to be able to retrieve S in case you forgot it, but you're afraid that some of the backups might get stolen and then people will find out what S is. So what you're going to do is break a secret into shares. You're going to store it in n places such that retrieval of at least k is required to figure out what S is. And if you get fewer than k, then, so if only 3 of them get broken into and k is 5, then S is not revealed. So the first simplest thing is if you have n locations where the quorum is 1, it only requires 1 to do it. That's very simple. You just store the secret in each of n locations. If you want to make the quorum be n, such that you have to be able to retrieve it from all n locations, then it's very easy again. You put random numbers in n minus 1 of them, and then you take the secret exclusive word with all of those random numbers in the last one. But what about if k is between 1 and n? So what you do is you choose a line, and if you have a line where the secret is where it crosses the y-axis, then any 2 points will reveal the line, and any 1 point gives you no information at all. So you do this by choosing a random number b, and the equation of the line is y equals b times x plus s. So s is the value of the line at x equals 0. So here you have a line. You can give as many points on the line as you want, and once you know 2 of the points, you know where it crosses the y-axis. And so the shares you give to people are the x value and the y value at various places on the line. So what you store is I comma y sub I in the first location, j comma y sub j in the second location, and so forth. And so what if 2 is less than k is less than n? And so what you need to do is create an equation of order k minus 1. So given any k points, the equation can be solved and S found. And so the math is you choose k minus 1 random numbers, b1 through k minus 1. The graph is going to be y equals S, the secret, plus the first random number times x, the second random number times x squared, and so forth. Now, real numbers are kind of annoying with computers and all that. And even integers are kind of annoying because they can get kind of an unbounded size. So in general, in these sorts of things, you do arithmetic mod some prime p, which will be greater than the secret. And a share is an xy pair where x and y are integers mod p. And you don't even have to give people an x share, because you could say, you're my friend number 7, so I'll give you the value of y at x equals 7. So this is not only mathematically cool, but it's very useful and practical. Okay, the next one I'm including just because it's just so cute. It's called bit commitment. So the problem to be solved is that Alice and Bob are getting a divorce. This won't solve that, but the problem is they can only talk over the phone, maybe because there's restraining orders or something, and they have to decide who gets to keep the house. So they're going to flip a coin. And whoever wins the coin toss will get the house. So there's sort of two obvious protocols. The first protocol is Alice flips the coin. Bob over the phone says, I want heads or I want tails. And then Alice says, you won the house or you lost the house. The second obvious protocol is Alice flips the coin. Bob is supposed to choose heads or tails but not tell her, and then she says whether it was heads or tails, and he says whether or not he got the house. So obviously neither of these works because one or the other can cheat. So we're going to use cryptographic hashes. Just to review it, it should be infeasible to find two numbers that hash to the same value. And it should be infeasible to, given a hash, to find a number that hashes to that value. So the solution of our problem is that Bob chooses a random number R such that the bottom bit is a 0 if he wants tails and 1 if he wants heads. He sends that hash across. Alice flips the coin, reveals whether it's heads or tails, and Bob now is stuck with, he's committed to heads or tails based on sending the hash, because now he has to send the number that hashed to that. Okay, so now I'm going to get into kind of the hairy crypto stuff that's impossible to understand, but hopefully I will give you the intuition into it. So there's this thing called the circuit model, which is necessary for understanding the next two things I'll talk about, which is secure multi-party computation and homomorphic encryption. So the circuit model says that any function of a fixed size input and output can be built with a circuit with just two operations, exclusive OR and or addition and multiplication. So both of these, homomorphic encryption and secure multi-party computation, involve computation on data. And the way you sort of come up with one of these schemes is you assume that whatever program you wanted to do on the data has been turned into a circuit, and then all you have to do is figure out how to do these two operations, and voila, you've proven it works. So if you turn your program into a circuit, it's a lot of overhead. You have to expand the circuit for every single branch. So for instance, and you can't do infinite loops. So if you're looking for an item in a database, you can't do like binary search or something. You can't select one thing because you're working, as you'll see on encrypted data, you have no idea which item it is. So your program has to actually go through every single item. Think about how inefficient this is. It's about 1 million times slower to do a circuit than a normal program, not even talking about expanding all the loops and stuff. Plus, whenever you might have done a branch, you have to execute all possible branches. So, Anyway, keeping that in mind, secure multi-party computation, there's so many papers about this. The problem they're solving is n participants each have an input, and they want to compute a function of all of those inputs, but each participant wants their own input to stay secret, even though it's used in the computation. And an example of this is an auction, which is everyone has a bid, but you don't want anyone else to see your bid, and the function you want to compute is what is the winning bid. So the obvious solution is have a trusted third party who receives all the inputs, computes the answer, and promises not to reveal any of the inputs. So, the highest bid was X, and Joe, you're committed to paying X. But cryptographers want to not depend on a trusted third party. So there's several proposed solutions, all that are very expensive. And one is actually deployed in the yearly Danish sugar beet auction. So the outline of one of the solutions is that each participant does secret sharing of its own input into n K-shares, where a K-share is you did a degree K equation, so the quorum will be K plus 1. So the shares of participant J's input, his input is I sub j, and the shares are ij1, ij2, ij3, and he gives one of these shares to each of the other participants. So each participant now knows n things, which is a k share of each of the n inputs. So participant 3 will know I sub 1, 3, I sub 2, 3, and so forth. So if k plus 1 participants conspired, they could calculate all of the inputs. So this isn't really encryption in the sense that you would think. So the assumption is, yeah, that won't happen. So now you have to turn your program into a circuit with operations addition and multiplication. Each participant operates on their own share of the inputs, and at the end of the computation, each participant will have a k share of the answer. So the way you add two inputs, let's say that if the program says to compute I5 plus I7, each participant adds its share of I5 to its share of I7, which results in sort of an equation where the answer is going to be the sum. So, I mean, this is incredibly cool, and it just works. That you can just add the two things, and your answer that you get will be a share of the other one. So if it were just this, it would be like really cool. The problem is multiplying. When you have two things, I5 times I7, yes, you can multiply them together, but now the equation, the order isn't k, it's 2k. And if you ever sort of do enough multiplications so that it's greater than n, no one will be able to recover the answer. So suppose there were a trusted third party. Once you had these 2K shares and you want to reduce it down to K shares, everyone could give their 2K shares of I5 times I7, and he could compute the answer, redistribute it as K shares, and everything would be great. But if you had a trusted third party, why would we be fooling with any of this stuff? So if you notice kind of the computation that it has to do, the third party, in order to create K shares out of 2K shares, is linear operations, basically just additions. So these can be done in a distributed way on K shares of the 2K shares. So, but it's very, very expensive, both in terms of computation and network bandwidth, because every time there's a multiplication that happens, everyone has to kind of distribute things around, do an expensive amount of computation and whatever. So my summary of secure multi-party computation, of which there's like so many papers written, is it's not a very important problem. And it's sufficiently expensive that it's impractical, even though there's this use case that it's actually being used. Given that there's not that many sugar beet farmers, and it only happens once a year, they kind of don't mind that it takes hours and hours to do kind of a simple thing. Okay, so homomorphic encryption. So the idea is you encrypt your data and you do operations on the encrypted data, and the answer is the encrypted answer. So this way, it sounds great. You can store your encrypted data in a public cloud that you don't really trust. And instead of downloading all of your data into a more trusted environment to do the computation, you can actually do the computation in the cloud. And fully homomorphic encryption says that any program can be done on this encrypted data, and the result will be the encrypted answer. You could download just this encrypted answer, which is small, and decrypt it locally, and the cloud never sees your key. It sounds really great, but don't get too excited. It is completely impractical. So the encrypted data and the computations are about 5 or 6 decimal orders of magnitude less efficient than doing computation on the plaintext. So every bit of plaintext turns into like a million bits of ciphertext. And they say, well, we're making it more efficient, but more efficient is not enough more efficient that we should worry about it. And then not only is the data much bigger, but converting your algorithm into a circuit is also mind-boggling, as I talked about before. So what about partially homomorphic, where there's only certain operations you can do? And sure, there are examples of that. So for instance, suppose you wanted to just be able to test for equality of your encrypted things. So the way you do that is ordinarily when you're encrypting, you want to use an initialization vector to kind of throw randomness in so that the same plain text will have different ciphertext. But if you want to be able to test for equality, just skip that step, and so that the same plain text will always have the same ciphertext. So sure, you can do that, but that will leak information, obviously. Another cute thing you could do is order-preserving encryption, where you can actually test two things to see which one's greater, even though they're encrypted. And that's kind of really cool. So the way to do that is encrypt n items sorted from the smallest to the largest. So, just encrypt them with any old thing like AES or whatever, and then you create, let's say, a 128-bit result, but then you add to the high order part what number it was in the sorting thing. So for instance, 79 got encrypted to whatever's in the black there, but you append a 1 because it was the smallest thing, and then you append a 2 to the next one, and so forth. But this means that ahead of time, you had to know which one was 1, 2, 3, 4, and 5. If you want to be able to insert things later on, then what you do is you just pick a number for the first thing that you encrypt, hopefully kind of a medium number. And if the next thing is smaller than that, you pick a different number. So here, the upper thing was 373, 57, 62, and so forth. So now if you want to minimize information leakage, and let's say you only want authorized people to test for equality, and you want other people to just not be able to test for equality. So what you do is you add an extra key, and you encrypt everything after it's been encrypted for order preserving, and then give the key to people authorized to test for that. So here you had this order preserving encryption, like I had on the previous slide, and then you encrypt it with a key that people who are allowed to look at the order preserving can see, and but everyone else will just see completely encrypted stuff. So now back to fully homomorphic encryption. So remember the circuit model, so we have to be able to do multiplication and addition. And so we have to figure out a homomorphic scheme that can do both operations. So one homomorphic operation is RSA. If you do RSA without padding, and you take, if the public key is an exponent e and a modulus n, and the private key is the inverse exponent d modulus n, then encryption of x is x to the e mod n. And if you want x times y, you take the encrypted version, which is x to the e times y to the e, and it's actually x times y to the e mod n, which is really cool, but that's only one operation. So for fully homomorphic, all of the known schemes involve noisy numbers, where the encrypted number is kind of near to a legal value. But if you made the encrypted version exactly a legal value, it wouldn't be secure. So you have to kind of add noise to it. But then the problem is every time you add two things with noise, the noise doubles. When you multiply, the noise. So if it gets noisy enough, it won't be clear which value which legal value it's closest to, and it won't decrypt properly. So there were schemes that allowed doing a few operations, but then the noise would get too big. So the breakthrough was Craig Gentry said that actually what you could do is you can take your data that is, the noise is getting to be a little bit too much. You could encrypt it and then homomorphically decrypt it, which is like mind-bogglingly expensive, but it's proof that, ta-da, it is possible. So there's lots of papers, and it's absolutely impractical in terms of computation and data expansion, I claim. So now I'm going to talk about blockchain, which is so incredibly misunderstood. So what is blockchain? It's a word. It's actually two words, but yeah. There's this quote, when I use a word, it means just what I choose it to mean. And unfortunately, it is used for so many different things that it's very, very difficult to know what someone is talking about. So there's extreme confusion because people are using the term blockchain for lots of things just because there's so much hype around it. So if you, say that your thing is building on blockchain or it's a more efficient blockchain, then, you get venture capital and everyone's excited about it. So there's all sorts of hype, how articles about it, whatever it is being considered for all sorts of problems. Internet of Things, alternative to PKI for managing identities, real estate transactions, and my favorite was even the U.S. military is looking at blockchain technology to secure our nuclear arsenal. So, if once you understand the technology, which hopefully you will in another 15 minutes, it is so completely inappropriate for any of these problems. But anyway, the way that this blockchain, as originally conceived, it can only work because there's monetary compensation to a community of things called miners. Otherwise, why would anyone do this? So Bitcoin started as a paper by presumably some pseudonym and released as open source software. And the community, the open source community, agrees on modifications, so the details might change. There's really no spec, it's just the code. And if there was a spec and anyone could make their own implementations of it, it would be a disaster, as I'll show. So it sort of requires all of the miners having identical code. So the design goal was they didn't want to trust any known institutions. So instead, trust is given to a very large community of anonymous miners. Anyone can be a miner. You can download the software and start mining on your own machine, or you can actually buy a hardware rig, which is much, much faster. And miners are rewarded based on doing a lot of computation. And so the assumption is that the set of honest miners will be so huge and they'll have such an awesome amount of compute power that no set of dishonest miners will have more compute power than them. That's the entire trust assumption. But, if you think about nation states and things like that, there's no reason to believe that they couldn't swamp the compute power. So there's this public ledger where every transaction is recorded and world readable. So the payer and payee in a transaction are public keys. You're allowed to change your public key basically for every transaction just because, that gives you maybe a bit of privacy. So public key X pays public key Y some amount. So the format of the ledger is as a chain of blocks, where a block has the hash of the previous block, the miner's public key, because if you're the one that gets that block, you want to get the Bitcoin, so your public key, a bunch of transactions, and a nonce, which is a random number, and I'll explain what you need that for. So the ledger says that from transaction, let's do the blue one, from transaction X15, A pays C a certain amount of Bitcoin, and so X15 refers to the transaction that had the hash called X15. So The difference between the received quantity and the paid quantity, because in the transaction with hash X15, A received 74.92 bitcoins, but in the transaction 2 down, A is paying only 74.21, and so the remainder is kind of transaction fee, which is kind of a tip to the miner that gets this block, so they get the remaining bitcoins. And you can have multiple outputs. So a transaction, you're required to spend the entire amount. And if you don't want to pay somebody the entire amount that you got, you can have multiple outputs. So you, from transaction X18, D pays E 25.11 bitcoins and F 830 bitcoins. And that is a way of paying yourself change if you don't want to spend the entire thing in one place. So it's not really anonymous. The entire world knows the sequence of public keys, who paid who. The merchant is likely to know who they shipped the merchandise to. And there's other instances where who owns a public key might be known. And if you mine the data of A pays B pays C, it can give you a lot of information. So a valid transaction. Suppose A pays B, the output of a transaction with hash X. How do you know if that's valid? Because anyone could make up such a thing. So you have to, the transaction has to be validly signed by the public key that is paying. You also need to find the transaction that had the hash X in which A was paid that amount. Are they allowed to spend this? And then you have to search all the transactions in between to make sure that they haven't paid somebody else before they paid you. And there's no central authority. If there were a central authority, having a ledger that everyone agrees on would be kind of trivial. But Bitcoin wants to be completely distributed with no preordained trusted things. So where do Bitcoins come from, and how is the ledger agreed upon? So a block is a set of new valid transactions such that the block has a cryptographic hash that's very, very, very hard to compute. So Bitcoin tries to make sure that a new block will be found about every 10 minutes. If it's found kind of too soon, more than every 10 minutes, they make the hash harder to compute. And if it's too hard, the hash is less hard to compute. So the hash difficulty is adjusted so that there'll be a block about every 10 minutes. So remember, a good hash is like a random number. So if you give it input, there's a 50% probability if the top bit will be a 0 or a 1. The probability that the top 10 bits will be 0 for random input is 1 over 2 to the 10th. So currently the hash has to have 70 leading zeros. So that's like you have to try, if you want to create a block, you have to try with like 2 to the 70 different random numbers until you get one that just happens to have a hash with all those leading zeros. So you insert a bunch of valid pending transactions, you choose a random number for the nonce, you compute the hash. If the hash doesn't have 70 leading zeros, which with probability 1 over 2 to the 70 it won't, then you have to choose a different random number. So if you're lucky enough to be the first to find a block with a small enough hash value, you get rewarded with some number of bitcoins. So currently the amount of bitcoins you get is 12.5 for that block, plus whatever transaction fees there are. So what's the purpose of all these hashing? Anyone can be a miner. So the entire trust model is saying, well, the probability that any set of bad guys can get together and have enough compute power, we'll just have enough honest miners and we don't have to worry about that. So suppose a set of miners did have most of the compute power. They could undo transactions and create an alternate history. They can double spend the things they had. Basically, this would bring down the entire Bitcoin concept. It's also expensive in terms of network bandwidth, because when you pay for your cup of coffee with Bitcoin, that transaction has to sort of be flooded throughout the internet. Also, when a miner finds a block, finds the next block, that has to be flooded to all of the miners. If your transaction was not included in the winning block, hopefully it will be in some later block. And so it's a gossip protocol. Your node knows some others, and those nodes tell others, and so forth. So here you have some sort of network of just who's configured with who. And so whenever you receive something, you just send it to all the neighbors except the one you got it from. So there'll be, depending on how much connectivity here is, there'll be lots of, going around in loops and all this kind of stuff. Plus, it could be fragile. Like if that node happened to go down, it's now partitioned. Into some set that can't talk to some other set. So blockchain forks. It's possible for multiple miners to semi-simultaneously find a hash. So that means that there'll be two different blockchains, two different valid blockchains. And if a miner sees multiple of them, it takes the one that's longest, the number of blocks. So hopefully the network will converge on a single chain. But this can take several blocks. So the advice is not to consider your transaction complete, not to consider yourself as definitely paid unless you not only see that the transaction where you were paid is in block N, but there's 6 blocks after that. So that would be like an hour. So, until the transaction where A paid you is safely recorded, A can double spend with somebody else. So if the internet were partitioned, or the gossip protocol itself were partitioned, then miners on each side would happily be adding blocks to the blockchain. When the partitions rejoined, whichever side had the longest blockchain would win, and everything beyond where they forked would no longer be in the ledger. And any bitcoins that were mined are no longer there. So there was an example of a really bad fork where some people made new versions of the software that had harmless tweaks in it. But unfortunately, that meant that there was some sort of block that looked valid to the new code and didn't look valid to the old code. So the ones running the old code just completely ignored the blockchain that had the invalid looking block in it, no matter how long it got, given there was an invalid thing. And this would have lasted forever, except, luckily whoever is managing this noticed it within just a few hours. Then somehow, magically, they were able to kind of contact all the miners and get them to switch back to the older version. Again, if this technology really took off, how would you let people know, whatever. So if there were lots of different implementations with subtle differences, there'd be forks like this all the time. There's also finite total Bitcoin. So initially the reward for finding the winning hash was 50 blocks, Bitcoins, and then it was halved to 25, and now it's 12 and a half. So every 4 years the reward is halved, and eventually the reward will be 0. But it will be negligible long before then. So they wanted to do this for, economic reasons, that there'll be a finite amount of these things. Now, transaction fees. The Bitcoin enthusiasts say the greedy banks take like 3% on every credit card transaction, but with Bitcoin, it can be like much cheaper. And today it's true, most transactions don't include a transaction fee and still get swept into the blockchain. But if there's too many transactions per unit time to fit into the finite size block that happens every 10 minutes, then the miners are only going to choose the ones with the highest transaction fee. Every transaction is work for the miner, because you have to do all of this hashing, and hashing over a smaller amount will be less work, especially you have to do it 2 to the 70th times. Every byte matters. And as the reward depends on fees rather than this, block reward, the transaction fees are going to have to rise to compensate for the lack of reward in there. So currently, it's about $5.85 reward per transaction in the block that the miners get if you count both the transaction fees and which is only like 3% currently, plus the other thing. So, interesting statistics. There are various websites that you can go to that says like how many miners there are and so forth. Now, full versus lightweight nodes. So the ledger currently, the blockchain is like, 75 gigs. I have it on a next slide. So imagine if your smartphone, in order to accept Bitcoin and in order to see whether it's a valid thing, you have to be able to look through the whole history. Imagine if you had to store it. So instead, it kind of changed into there's lightweight nodes and there's full nodes. A full node keeps the entire ledger, and if you get paid a Bitcoin, you go and ask a full node, hey, should I believe this? Is this a valid thing? And they'll check against the, so you're configured with some number of full nodes, which is kind of ironic because supposedly nothing needs to be trusted, but you really do have to trust the full node that you're configured to trust. So how much energy? Well, the assumption is in order to compute how much energy, it's very hard to compute this sort of thing. So this is based on capitalism, that if mining was very lucrative, more miners would join, and if the cost of electricity is more than the reward, miners will drop out. So the amount spent on electricity will be a little bit less than the reward. And it's hard to know exactly how much it is, but the miner reward over the last year has been about $1 million a day, and there are reports that the miner reward barely covers the cost of electricity. And so at 10 cents per kilowatt hour, this is about enough electricity for 200,000 American homes, or about half a nuclear power plant for this technology, which is just kind of a little researchy thing right now. But I actually claim that number is too low, because if you actually go on Amazon and buy a mining rig for $800, you want to use it, even if you're actually eating up more electricity than you're getting. You also may not really be conscious of how much your electric bill has gone up. And there's countries where electricity is highly subsidized, so mining is way cheaper. And you may be stealing the electricity, so you may not care, like if it's done with bots or invalid cloud accounts. And those cases, it's software, and it's harder to win against specialized mining machines, but, if the electricity is free, why not? So how much storage? It's about 85 gigs. It grew 40 gigs in the last year. And there's 5,000 full nodes that are all storing this. And hey, I work for a storage company. This is great. But they're talking about increasing the block size, which will mean that the ledger will grow like even bigger. And this is stored at every full node. And also, whenever a full node comes up, it has to download the entire thing. It's also hard to protect your Bitcoins. So I do not keep my money in a mattress in my house, because I assume that a bank is kind of more capable of storing it safely than I am. But if you have Bitcoins, it will be stored on your computer. So there's two possible problems. If somebody breaks into your computer, and when has that ever happened, they can steal all of your Bitcoins. Or if your computer dies and you haven't made enough backups, the money is just gone. So anyway, the reason I'm not a fan of this technology is it's enormously wasteful of energy, bandwidth, and storage. And imagine if it really caught on and people really did start using it for Internet of Things and all these other things. Transaction fees will eventually need to be really large. It's fragile, especially if there's any diversity in implementations. This trust model is just weird to me, that it's based on having enough compute. And it's difficult for a user to protect their money. It's likely that they'll just lose the information or that somebody will steal it from them. When you pay a coffee shop for a coffee, do they have to keep you there for an hour to make sure that it's really validly recorded in the ledger? There's a permanent record of every transaction, and there's a limited number of transactions per unit time in order to fit into this. So what do people think are the good things about this? Because there are enthusiasts, and they say, well, it's a distributed ledger. It's not just in one place. I claim that people know how to store things in more than one place. There's no central authority. And I claim if you wanted to do something sensible is have several trusted authorities. So instead of one bank, have 20 banks with maybe some from different countries. And a transaction is valid only after a majority of those have signed off on it. That's perfectly reasonable technology. No greedy banks taking 3% transaction fees, and I claim Bitcoin transaction fees will soon be much worse. There's an immutable permanent record, and you can do that with digital signatures and storing things in multiple places. And proof that event X occurred at some time. Again, there's straightforward ways of doing that. I would claim there should be like timestamping services that you send them a hash, they timestamp it and sign it, and if you're afraid that that timestamping service will die or something or get corrupted, make sure that if you really want to prove something, you have to get it signed off by 20 timestamping services. So people are calling all sorts of things blockchain, some of which are totally reasonable technology, but they aren't revolutionary new technology, and they have nothing really to do with Bitcoin's blockchain. So thank you. So there's probably a bit of time for questions, but I'll be around for the whole conference, so feel free to talk to me about this stuff. I'm very passionate about it. Yes?
Hi, Radia. So there were two things that you talked about in a theoretical way that I'd like to clarify applications in the way that LISA attendees probably would think of them. And the first is in your discussion of splitting data and secure retrieval, whether that has anything to tell us about whether government backdoors can be made to work or not. And secondly, about auctions and circuits, does that have anything to tell us about whether black box cloud computing, where the cloud provider does the computation without knowing either the algorithm or the input and output involved, is possible or not?
Oh, okay. I don't remember the first because my head is very small, but the second one, right? The second one, yes, there is technology to do what you want to do with homomorphic encryption and secure multi-party computation. That can be done very, very practically, and it's something else that I'm really passionate about, and it's this thing that Intel will have in their chips. It's currently in client chips called SGX. But at any rate, that would enable you to do all this stuff in a straightforward, practical way.
The first part was if you have a quorum-based government backdoors. Yeah, government backdoors are sort of orthogonal to the other stuff, secret sharing and whatever can be done with a backdoor or without it. So anyway, I better go. Thank you.
I'll be around, so keep in touch.